Welcome back to another episode of A View from Earth, the official podcast of the Fiske Planetarium. I just gestured the Fiske Planetarium, which is behind me on my Zoom virtual background for any audio-only listeners out there. My name is Colin Sinclair. I'm an undergrad here at CU. I study astrophysics and computer science. And along with being one of the co-hosts of this show, I also present live and in-person shows at the Planetarium. So that's a lot of fun. And as always, I'm joined today by Tara Tomlinson. Hi, Tara.
Hi, Colin. I am back, and my name is still Tara. I am still a CU alum and a planetary scientist. I am now a graduate student at Dartmouth and a Fisker as well. I used to do presentations at the Planetarium and run our outreach program, and of course, host the podcast.
Pretty much anything you can think of that was happening at the Planetarium, Tara was helping with or doing herself.
Well, you know.
Today, we're going to talk to Dr. Craig DeForest, who is the PI of the Punch mission, which, as we'll learn as we dive into the interview, is studying the big picture relationship between the sun and the earth and the space weather that connects us. It was a lot of fun to record this interview. There was a lot of, I feel like, humanity that was kind of built into it, which, you know, sometimes we're, you know, kind of focus on the science heavy stuff, which is great, but always good to acknowledge, you know, the other things too.
Yeah, I thought a lot of the things that he had to say were not just scientifically interesting, but like you said, kind of human relatable. He talked a lot about, you know, coming from different backgrounds and including a lot of diversity in our science. He had a lot of really cool advice for young scientists, which as a young scientist, I thought was super neat. And he also, I noticed he had a lot to say about just like general leadership. We're talking to him about what it means to be a PI, a principal investigator of a whole mission. And he had so many cool things to say about, you know, bringing awesome people to his team and letting them be awesome. And, you know, even though he's the leader, knowing how to do all the little things too. I thought that was just lots of really great life lessons, man.
Well, and something, you know, to kind of tie the two together, being a leader of a team, you know, a big component of this Punch mission, again, as we'll talk about in the interview, has to do with outreach. And a question that I asked while we were interviewing, or maybe it was you, one of us asked a question to Craig about, you know, communicating the wonder that we as researchers, you know, feel for the work that we do. And sometimes that can be kind of hard to get across if we're focused on a very narrow, specific question that has arisen out of decades of experience in, you know, heliophysics. How do you get, you know, that excitement across to someone who, say, is interested in space but doesn't have a degree in, you know, in heliophysics?
Or doesn't even know what heliophysics is.
Yeah, what does heliophysics mean? I don't know. Yeah, so it was a cool, and I think his response, which I'll leave for him to say, it felt fresh.
Yeah, I noticed a couple times instead of saying, you know, science does this and science does that, it's not science, it's just generally cultivating a sense of wonder.
Absolutely.
That's what science really is, and I like to think of it that way.
I also loved the quote. We have a nice discussion about imposter syndrome, you know, kind of like what you were saying, who gets to do science and, you know, who should be able to do science. Something that Craig said was oftentimes you have to enjoy feeling stupid because you're in a room with people that have been doing this 3-4 times as long as you have. And there's always questions to ask. And, you know, sometimes I have to stop myself and ask, like, wait, is what's happening here? And the truth is, you know, hey, if you enjoy just learning constantly, then you're good to go.
Yeah, as a first year grad student, I can absolutely relate to that statement.
Graduate schoal. Finally, I think before we really jump in, I just want to make a disclosure that having chickens is not equal to having a farm. At the end of the interview, I asked Craig about his farm, and he was very surprised and said, "I don't have a farm." And I was surprised because I was like, "Oh, I was told that you do." As it happens, Craig is the owner of some chickens, which evidently does not constitute a farm.
A
They're
handful of
different.
chickens does not equal a farm.
Correct. And I don't know why I had farm written down in my notes. I just did. And so that's on me, everyone. My apologies.
Chickens do not a farm make.
Oh, well said. Well said, Tara. Yeah, love it. Cool. Well, anything else you wanted to talk about before we jump in?
No, I think we should let these people hear this awesome interview.
Let's do it.
All right.
Dun, 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 dun. All right, and now we are speaking to Dr. Craig DeForest, who has studied the sun, its corona, and the solar wind for over 30 years. Currently, Dr. DeForest leads the Heliophysics division at the Southwest Research Institute in Boulder and is the principal investigator for NASA's PUNCH mission, a NASA small explorer mission to better understand how the mass and energy of the sun's corona become the solar wind that fills the solar system. He is well known for his expertise in solar data analysis and reduction, and is also the vice chair of the American Astronomical Society's Solar Physics Division. In addition to research, Dr. DeForest also has a passion for outreach, and PUNCH's outreach plan includes collaboration with 5 planetariums and science centers, plus other cross-cultural partners to activate an ancient and modern sun-watching theme that will engage historically marginalized populations. Dr. Craig DeForest, thanks so much for being with us today.
Oh, thanks for having me.
So I guess we'll start off with a question that I'll let you answer more in depth, which is, what is this PUNCH mission?
Aha. So PUNCH is, it's not a telescope. We're used to flying telescopes in space. It is a mission to image the sun's corona and the solar wind as a single thing. So I'll back up a little bit. The sun is not just a static star. It's constantly moiling and shifting. More importantly, the outer atmosphere of the star is constantly streaming out into space. It loses something like 1 million tons of material every second. It streams out at hundreds of kilometers per second, 300 to 700. So what is that? 200 miles per second up to about 500 miles per second. Across the solar system. It sweeps over everything in its path, including the Earth. And so people have studied the solar wind for a very long time. Well, very long, 70 years, ever since the dawn of the space age. The way we study it is by generally flying a spacecraft into the wind and sampling it. And that allows us to learn everything about this material that left our star and hurtled across the solar system, right in the one place where the spacecraft is. Now, if you think about studying the wind on the Earth, well, you can do that. You can stick up an anemometer, you can sample the air pressure and the temperature, you can measure some things about it, and you can know everything there is to know about the air in that one place as the wind blows over you. But that won't tell you about large-scale weather patterns, right? You can set up hundreds of those stations, or even better, you can launch a satellite to look at the entire weather system as a single entity. Well, in the run-up to designing and proposing PUNCH, we realized that it's possible to image the solar wind itself. It's a very tenuous stream of material. There are about 10 atoms per cubic centimeter, 50 atoms per teaspoon near the Earth. Here in
Which,
my
to be
room,
clear, is a very, very, very small number for people that aren't familiar with how much stuff there is.
Right, so there's 100 billion molecules in a teaspoon near me.
Oh
right?
my gosh.
So it's very tenuous. It's the closest thing there is to empty space. Well, it is empty space, but there's material in it. It acts like a wind. So those particles that are in there, those atoms, are ionized. So there are free electrons floating through the void, streaking out through interplanetary space. Those free electrons reflect sunlight, and we can actually image, we can photograph the solar wind itself. It's extremely tenuous stuff. And it's remarkable because we can see weather patterns. We can see things that get ejected from the sun and transit the entire sky across the void. This is a medium that we as a planet are immersed in. It sweeps over us all the time. So So punch is an attempt to image the relationship between this material and the sun's outer corona, so the outer atmosphere of the sun and the solar wind. These have been studied for 50 years as separate things, and for the first time we'll be able to image them directly as a single unified system. It's very exciting, well, for me.
That
I
is
would say
very
so.
exciting. I have to ask, because I do a lot of remote sensing stuff, how do you image something that's only 50 atoms? That's very, very little. How do you see that? What does your instrument do?
That's a great question. It's the secret is that there are a lot of teaspoons in deep space. So there aren't very many electrons in a given teaspoon of empty space, but there are a lot along a given line of sight. Even so, the light that we're imaging is about 1,000 times fainter than the Milky Way galaxy. So if you've ever been out on a dark night in a dark place, like around Boulder here, you can see the Milky Way on a moonless night. Think something that's 1,000 times fainter than that. So the things we see, your eyes could totally image, right? They're large and sweeping across the sky. The field of view of this instrument that we're building is 90 degrees across. So it's a good fraction of the sky. And your eyes could totally see anything that this instrument can resolve, except it's just too faint. You're not sensitive enough to see it. So the easy part of this mission is flying optics that can produce the images. The hard part is subtracting the background and foreground. We have to remove the star field and the Milky Way and air glow and half a dozen other effects with extreme precision in order to measure the faint light that's coming in.
I remember learning about a process that does that sort of thing just on your typical ground telescopes that will, I forget what it was called, but it would react to changes in the atmosphere to kind of undo any distortion of the atmosphere causes, to the light coming into the telescope. And something that we talked about was how quickly it had to respond to measurements of the ground's movement and the atmosphere. Are you doing the same thing with this? Are you measuring everything else simultaneously with time, or is it more of a, we understand this to behave generally, and so we can subtract it like that?
It's more the latter.
Okay.
We are launching Punch into space. It's 4 separate instruments, and we can talk about why, that work together as a single large virtual instrument. But in space, there's much less variability. And so we can use the difference between what we're looking at and the steady star field and the steady stray light that leaks around the baffle in order to remove those effects. The baffles, by the way, are incredible, right? These things are exposed to the eternal noontime of space, and they have to view things that are 17 orders of magnitude. That's 0.17 zeros with a 1, fainter than the surface of the sun itself, right? So the front of the instrument is in noontime being shone on directly by the sun, and a meter away we've got a camera looking out the side that has to be darker than the darkest night you've ever experienced. It's an engineering feat. We can't even test the things in air. We build the baffle, and when we want to test the stray light that leaks around from quantum mechanical effects, we have to put it in vacuum because air molecules scatter too much light. We can't shoot a beam over the top without it scattering in.
So this seems like a question that I have asked a few people now, but it seems like a scientific, like you said, it's a feat of engineering, but it seems like there's also would have to be a lot of correspondence with the scientific team, so between, the people building the instrument and the scientists like yourself that are using what it gives you. Mm-hmm. Are you able to just say, here's what we need in that kind of situation, and then engineers build it, or is it an ongoing process where you kind of go back and forth and try different things?
At this point, we know what we need, but there is some negotiation early on, right? I mean, you start with a scientist who has an envelope, right, and scrawl some stuff on the back of it, right? I think I could do this, and then you iterate and do simulations, think very hard about what exactly do we need in order to make the measurements we need. You go back and forth. Engineers hate that. They just hate it. What they want is a collection of requirements, and deriving those requirements from your scientific, curiosity is hard. Every scientist wants more, right? And so then the question is, how much do you actually need? Well, we spend a long time kind of working that out.
Got it. Well, I feel like this is going to end up being a great conversation, but really quick, before we get too far into the depths of what Punch is, I want to ask what your role with Punch is as Dr. Craig DeForest.
Okay, I'm the PI. So at some level, I'm the leader of the mission. At some level, it's my job to sit back and watch for difficulty across the project. As a scientist, as you both know, you have to have a lot of different skills, right? You came here to probe the secrets of the universe, right? And so first you have to learn how to speak the language that those secrets are expressed in. And then you have to conceive, a measurement that you'd like to make that will teach you something about the universe. And then there are several steps down to, why is this bolt jammed in my telescope, right? And so the most important thing for what I do is to try and keep everything in my head at once, as much as I can across those scales, right? So that nothing ever comes to a PI's desk unless it's already a problem, right? So you kind of have to, and if you're good, you've collected a team of people who are excellent. So it's a hard problem, right? So it's your job to kind of adjudicate across the different levels of abstraction in the project to kind of decide, oh, this problem is so hard that we need to adjust a requirement or change something else about the mission to solve that problem. Or, oh, it turns out this isn't a problem at all. Somebody told you something that was too strict. And so that's not really a requirement for you, right? Something that was new to me for this mission, this is the largest project I've ever managed, is just the level, how important it is to manage a team and its interaction with the customer, who in this case is NASA, right? It turns out that is a skill that's separate from the skill of doing science. And it's trainable, but it's a very different thing from doing science. So I think if we have any budding mission PIs in the audience, right, the secret is to be as much of a Renaissance person as you can, learn as many different things as you can. I came here because I'm interested in the outer atmosphere of the sun, but today I was looking things up in that famous old book, The Fundamentals of Astrodynamics, because I needed to calculate, how many meters per second of rocket fuel do we need to keep station for our spacecraft, right? And I have people on the team who do that. But it's important that I have a sense of it, right? So I have to go do these things in the background.
How much of your job would you say is that sort of delegation and problem solving that's worked its way up versus asking your own scientific questions, or working with the team to ask the scientific questions? What's the balance like as a PI?
That is a really good question. It varies a lot with time. In the earliest stages, as we were putting together the mission, it was just 3 or 4 of us who were interested in these problems and trying to address, what could an instrument do conceptually. But as the team has grown and as we've refined our science questions, I've stepped away, right? We have a wonderful project scientist on this team, Dr. Sarah Gibson, who's over at HAO, High Altitude Observatory. And she's corralling and marshaling the various scientists and making sure that the questions are addressed by the science program we've laid out. And so part of my job is to allow her to be excellent. Right, so at this particular stage, when the mission is in development, it's almost all problem solving. But of course, early on, it was all brainstorming and developing what can we do. After we launch, of course, I'm just as eager as anybody else to get my hands on those juicy data.
So getting back to more of what Punch itself is doing, this also has a lot to do with this hot word, space weather, that we hear about a lot. That's kind of a big thing now. So what is sort of the big picture goal for Punch in terms of this space weather monitoring and things like that?
Sure. Well, let's see. So I'll back up a little bit as to what Punch is doing in more detail, and then segue into how that helps us with space weather. So one of the things we're doing with Punch is, let's see, Punch is an imager. I want to back up a little bit. And the problem is it has to look at things that are very different brightnesses. Close to the sun, the zodiacal light, that's light that you see around the zodiac, which is made by dust that's orbiting the sun, is very bright. The zodiacal light is quite bright close to the sun. You normally don't think of it much because the sun is very bright itself. And so when you look directly at the sun in the sky, you don't see the zodiacal light, but it's there. And it forms a very bright background. And so at the outer reaches of our field of view, very far from the sun, 45 degrees from the sun, the background is 10,000 times fainter than it is at the inner part of our field of view, just 1 degree away from the sun. So we're imaging this annulus from close to the sun out to 45 degrees away, so we can see things streaking all the way across the solar system. We have to break that field of view into at least 2 different instruments, because 10,000 is too much. A factor of 100 we can manage. So we have an inner instrument called the narrow field imager, NIFI, which is a coronagraph. Now, a coronagraph is a special kind of camera. In essence, it's an ordinary camera with about a 15-degree field of view. So if you're a photography buff, it's sort of a longish lens, not a huge telephoto, but a little bit of a telephoto lens. The field of view is about the size of the constellation Orion, for reference, if you're used to looking at the night sky. And in front of the aperture, we have a block of metal called an occulter that blocks sunlight. The whole thing points straight at the sun, and that little occulter blocks sunlight from entering the aperture, so that the instrument looks around the sun. So we see the entire annulus around the sun with one instrument. So that's a coronagraph. That's our narrow field imager. The other half is the wide field imager, which is almost the same thing, but in linear geometry. So we have a camera that looks up into the sky, and we have a deep baffle that hides it from the sun, and a straight baffle on the front. Instead of a curved cylinder, we have a straight flat baffle that blocks off sunlight. And that instrument looks out to 45 degrees, from 5 degrees to 45 degrees from the sun. The problem that we have with that instrument is that there's a darn planet in the way. We have to stay close to the ground so that we can get the images back down in a timely manner. And so we can't get too far from the Earth, but then the Earth blocks the view. We can only look up, we can't look down. So we have 3 of them spread out around the Earth in orbit. And each one is looking up, but up is in a different direction for each one. So they all of their images get merged together on the ground, all 4 instruments images. What we get from a single exposure, if you will, is a trefoil shape. It's like a 3-leafed clover on the sky. As these things orbit, the shape rotates around the sky, and so we build up the entire inner solar system that way. The other aspect of these instruments is they're measuring polarized light. So I mentioned earlier that electrons scatter light, and that's what we're looking at. Just like behind you, Colin, there's a bright blue sky, right? That's light that's scattered by the air molecules, right? Sunlight would have hit somebody else, but it hits an air molecule and bounces off into you instead. And so that's what's happening with the light that we're viewing. It's bouncing off electrons instead of air molecules. It gets polarized when it gets scattered. And the degree of polarization of the light that we're looking at, just how polarized it is, lets us determine the angle that it was scattered. That lets us produce not ordinary images, but 3D images. So if we see something crossing the solar system, we know where it is, not just, on a screen, but in the space between us and the sun. That's very important for your actual question, which is, what are we doing about space weather? So from time to time, the solar wind has these titanic explosions, huge clouds of material embedded in it. These are called coronal mass ejections. And what happens is near the surface of the sun, the magnetic field gets stressed. I don't want to go into all the details of why, but the churning motion on the surface of the sun energizes the magnetic field, which is confining a lot of material in a tight knot. When a system like that destabilizes, it hurls that particular cloud of material out into the solar system, goes streaking across the void. If it impacts the Earth, it can either bounce off harmlessly, or depending on which way the field is pointed, up or down when it impacts the Earth, which way the magnetic field is pointed, it can cause a geomagnetic storm. And geomagnetic storms are not much to look at. If you're looking at one with a compass, you can actually see a compass needle deflect a little bit with a big one. Kind of neat. Navigators used to have to know about that. But when that happens, that little subtle effect with a compass needle involves huge changes in the magnetic field of the entire planet for a little while, which turns anything big enough into an electrical generator. So one of these effects back in the middle of the 19th century actually lit the telegraph system on fire. Right, you had these long wires going across the American West out here to Denver area, and there was an enormous geomagnetic storm. Nobody knew what it was at the time. All they knew was that the telegraph system melted down, right? There were fires in stations all the way across the nation, and the telegraph didn't work anymore. So there are also effects on radios, power grids, astronauts, satellites, which we depend on. So we care a lot about predicting these kinds of events. If you know the event is coming, you can mitigate it. You can not trade as much power over your power grid. You can put your satellites into safe mode, this kind of thing. So there's a huge effort to predict space weather. But where we are now, we don't have the ability to track these storms as they cross the solar system. And so it's hard to know when one will hit, if it'll hit, or if it does hit, how strong it will be. And so Punch is, in some sense, a weather satellite for space weather, because for the first time, we'll be able to see the entire system, just like weather satellites allowed us to see the whole weather system. We can track these things from sun to Earth directly.
And will this be a real-time continuous observation of the space weather situation, or will it be like an incremental report? Here's what things look like right now, and then tomorrow we'll look at it again.
Both of those things.
Oh, great.
So Punch operates on a 4-minute cadence. So we get an image of the sky every 4 minutes, a polarized image, full polarized image. And that's important to the science because we want to track how things change and evolve as they move. But it's in low Earth orbit, so we only get the data on average once a day. So you get a whole day's worth of data once a day. Now we're working with the Space Weather Prediction Center over at NOAA, right behind your right shoulder, I guess, to produce a low latency data product. And if that all works out, we may switch to a mode where we have pass every hour, basically once every orbit or so. And that'll allow the data to be used not just for science, but also for real-time forecasting.
Very cool. I'm going to ask, as someone with decades of experience, we mentioned earlier that you had over 30 years in the field of solar research. What role outreach plays in space science? This seems to be something that is important to the Punch mission. And so I'd like to open the floor for a discussion of outreach in space.
Personally, I feel that any space program, including Punch, has an obligation to reach out to the general taxpayers who are paying for it and tell people why they should bother. I mean, Punch is not very expensive for the average taxpayer. I think it costs everybody 3 cents. But on the other hand, I really want to make sure that everyone gets their 3 cents worth of information about the universe, right? We want to share both why it's useful and also why it's exciting. We want to share that wonder with people. I mean, you do things like this for several reasons, right? There are societal reasons. We'd like to understand our environment, predict things like space weather. There are pure scientific reasons, right? We'd like to know more about the sun as a star and how stars work. And of course, that comes home because Deborah Scherer, an old mentor of mine, used to say, the sun is the only star in the universe that's been proven to grow vegetables, right? There's a direct connection between the sun and its outer atmosphere and us, right? This is where we live. And so we'd like to know more about it. So there are a whole host of reasons of that sort. Why people go into this field individually is that sense of wonder, right? Where you guys know this, you're scientists. We go into our fields because we're called to it. We are infused with a sense of wonder and curiosity about the world around us. And so my personal reasons for doing Punch are different maybe than the society's reasons, but they're very important also. And it's important that we cultivate that sense of wonder in order to continue growing as a society. So that's not quite the question you asked, but that's why outreach is important to me.
And I think you kind of touched on this with the sun is the only star that is confirmed to have grown vegetables. But it seems like Punch is kind of pushing this sun watching theme. Can you say a little bit about that?
Certainly. You know, people have been curious about the sun as long as there have been people, right? And so we wanted to connect that idea to the science we're doing, right? It's very easy for a mission like Punch to get lost in the details, right? We are doing some really amazing technical things. You know, the team that are putting together the instruments I already mentioned, right? Where they built a baffle that attenuates sunlight by 17 orders of magnitude, right? That's almost a billion times, right? In the space of like a foot. That's incredible, right? But nobody cares about these things, right? That's just a neat thing some egghead did somewhere, right? What's really interesting to almost everybody is, you know, what is that thing that rises in the east every morning, right? People have been wondering about that for as long as there have been people. And so when we started working with Dr. Sherilyn Morrow, who's leading the outreach effort, she had some prior ties to Chaco Canyon and brought to our attention this amazing petroglyph that we think is the first recording of the solar corona in a durable medium, right? This is a petroglyph that's different than the kinds of things people drew on these rocks over time. It dates to about 1100, 1097. And in 1097, we know there was a solar eclipse there. And so, you know, we normally think of science as something that's, or wonder in the world around us as something that's the province of modern people. But it's not, right? People have been wondering about the world for as long as they could, right? You know, look at some phenomenon like an eclipse. If you can see it with your eyes, you can wonder about it and formulate ideas about it. And so this has been going on an extraordinarily long time. And man, I love that because it ties us together across cultures, across time, right? Imagine being somebody alive in America or in Europe in 1100, right? And there's an eclipse. I mean, they're mind-blowing enough now, right? What would you think about something like that? How would that change your vision of the world around us? And so I'd like to use the data from Punch and present the data from Punch in a way that people can just understand these images, right? We are embedded in something, right? This space environment around us isn't something distant like you know, a galaxy or like Betelgeuse. This is something that's here and now and sweeping over us all around us all the time, the solar wind. And so understanding, you know, this is an aspect of our environment that maybe we don't see with our own eyes, but it's there nonetheless. That's really cool to me.
It is super cool, I think. In particular, Punch seems to really be wanting to push this involvement and incorporating historically marginalized groups and indigenous populations too as the PI. Why is this sort of an important push for you guys?
Well, this is important to me, again, personally. I mean, there are lots of societal reasons we want to do this. But again, science is not the province of middle-aged white men, right? I'm one. But we need to bring everyone on board. You know, people come in from different cultural heritage. People come in with a different set of circumstances as they grow up. This makes them think differently. And science is a team sport. We need everyone's insight to continue advancing. And so on the one hand, I'd like to share the wonder of the systems we're studying with people who otherwise might not see it. But also, from a selfish point of view, I want to make sure that the next generation gets the insights that come from as wide a variety of backgrounds as possible. And so reaching out to folks who otherwise might not even think about the sun as anything but a source of light, you know, whether they be, you know, whatever race, whatever gender, whatever economic background, and getting people turned on to the wonder of the science and the fact that this is something that people like any of us, right? There's no, I'm not like that person, right? Anybody can do this kind of work, and anybody should do this kind of work if they're called to it. And so I want to make sure that people have the ability to hear that calling.
Is there a way that somebody, anybody, my mom or whoever's listening to the podcast could maybe kind of get involved or keep up with what you guys are doing? Is there like, do you have any sort of like citizen science involvement or anything like that?
We don't at the moment, right? We're in mission development, but we do have citizen science activities planned. We are affiliated with the Eclipse 24 efforts. And so we'll be helping to do outreach for that and helping people set up citizen science for that. The punch data are available to literally anybody. We're making sure that there's no proprietary period. The images that we make will be made available so anybody can inspect them and do science with them. Our science teams are open to the public. So if you have the science background and you're interested, you know, you're welcome to join us. If you don't feel that you have that background, there will be programs that we develop to try and help give people a leg up into understanding and even making discoveries with these data.
I'm curious, Craig, how I think something that a lot of educators, especially in STEAM, struggle with is connecting that wonder that we feel as scientists to, you know, everyone else who maybe doesn't experience that firsthand, you know, intuitively or right away.
Sure.
Does Punch, I mean, you as Craig or as the PI of Punch, what techniques do you use to kind of bridge that gap between your own excitement and your team's excitement and, you know, the people that you're trying to reach?
I think part of it, that there are different levels to communicate to different audiences, right? For folks who have a background in the sciences and know calculus and have maybe done some digital image processing, the way we communicate is different than we might communicate to somebody who has a passing interest but doesn't want to spend the years that it takes to become a solar physicist. And so with punch data, we're working very hard to distill the images. I mean, fundamentally, we're a camera, right? We're making a camera. It's a fancy camera, but that's really what it is. And so just by showing people, you know, this is what's going on in the world around you, we hope to sort of stimulate that interest. But, you know, we can go deeper than that. We can say, hey, look at these things. There are wondrous things to see that, you know, we can explain why they're shaped the way they are, or maybe we can't. right? That's why the scientists are in it, is because there's the unknown and we like to find new things. But to share that journey with people, it's interesting. I remember seeing here at Southwest Research in Boulder, I remember sitting in a conference room when some of the first images from might have been the Eros asteroid flyby were coming in. People were looking at them on the screen. And it's a room full of planetary scientists, right? And the most common thing you'd see is, how did that rock get there, right? Right? We ask these really basic questions, and we dress them up, and the tools to really address them deeply take a lifetime to master, right? But you can still ask the question even without those tools. And if somebody answers the question, they better be able to explain it to folks who didn't spend a whole lifetime deriving those tools, right? That rocket got there because it was another asteroid and it had a low speed impact and stuck. Well, why did it stick, right? These are basic and deep questions. I want to get away from the idea of a scientist as somebody who is endowed with the inspiration of the deity or something, and get back to the idea that it's a person who put in the time, right? There was a Rock Johnson movie recently that I just loved. It was, what was it, High School Reunion or something, right? And the little nerdy guy, like, gets picked on in high school and then turns into the Rock. And one of the other characters says, "How'd you get that way?" He's like, "Well, I just worked out 6 hours a day for 20 years. Anyone could do it," right? So scientists aren't special except that they've put in the work, right, to be able to speak these weird languages. But you can't allow that to disconnect the scientists and the endeavor of science from our roots, right? We need to be able to explain what we're doing to our grandparents who maybe didn't go to college.
Taking a look at, earlier we were talking about how a diversity in backgrounds and thinking is beneficial. Unlike a lot of other people whom we call scientists, you received a Bachelor of Arts in Physics from Reed College, a liberal arts education. How does that compare, or rather, how does that, what does that look like today in comparison to colleagues of yours who perhaps had a STEM undergraduate education from a hard research university?
Well, there was nothing that was not rigorous about Reed College, I can tell you that. But a lot of what we do in college, especially if we're bound for the academic professions, is learn how to think, right? And it's very important to be exposed to all aspects of that. That's why liberal arts was invented, right? Is to teach people how to think. There is a difference between the kind of thinking that you learn in, say, a classics class, from the kind of thinking you do in a calculus class, right? And they're tied together, but both of those are important in order to make progress in the world. I feel that pretty strongly, right? People ask me, what was the most important course you took in undergrad to advance your physics career, right? And journalism, right? English literature, right? These things are very important. If we go into the world and we extract the secrets of the universe and we can't communicate them with our fellow beings, we haven't really done anything for humanity. We've just, passed some time in an amusing way. And so I think liberal arts education really helped me anyway to realize that. That was really the biggest thing that I probably took out of Reed was the fact that somebody doesn't know calculus or didn't get called to go down a particular pathway doesn't mean that they're stupid. It doesn't mean that they're ignorant, right? It means they took a different path. And that works both ways, right? If you have a different path than a physics major, it doesn't mean the physics major is a brainiac. It doesn't mean, anyone should look down at you, right? We're all humans. We all approach the world in different ways, and we're called in different directions. So I encourage folks who are thinking about a career in STEM to really focus on some broadening themselves in undergraduate, right? Take a classics course or two, take a literature course, take journalism, study history, study European history, Asian history, right? Get used to thinking in those different ways, and those tools are available. Likewise, if you're not called to physics or astronomy, you should still take an astronomy course, right? For the same reason.
Especially astronomy too, because I think a lot of I LA'd for, or basically undergrad TA'd for, an intro astronomy class for non-majors, and I have to say, as a gateway to kind of STEMmy, sciencey stuff, astronomy is the way to go.
Oh yeah.
Yeah, we even see it here at the planetarium. People just, anybody from off the street will come in and can be amazed by the stars and the sun and the planets. It's great.
Exactly. And it's funny, I used to get a question a lot, and you probably get it too. If you study something as a physicist, isn't that like, don't you lose the beauty of a rainbow, right? Or gorgeous mountain scene? It's like, no, right?
Not at all.
If you know why rainbows exist, that just makes them better.
Exactly. I had that exact conversation with somebody about a sunset. It's just like, just because I know why it's all these different colors, I think that makes it even cooler.
We can tell by your hair, right? That's
yeah,
awesome.
exactly.
Yeah, right. I will say there have been times after, thinking, like starting to think about how everything is a collection of smaller things, which are in turn a collection of smaller things. Every once in a while, I'll overwhelm myself and like try to think about all of it at once and be like, nope, I have to stop there, because if I keep trying to think about the whole thing, I'm gonna like crash or something, like a computer.
But actually, that's really important, right? Stretching your mind in that way is huge, because like in almost any field, but particularly in the sciences, the most important thing to do is to connect from these big giant questions, right? Why is that sky blue, right? Down to the very detailed things you have to do to answer that question, right? And being able to carry both of those in your head at once is something you have to learn, right? It takes effort.
Absolutely. And that's something I think that we struggle with as students. I remember even when I first started, I have an undergraduate degree in English before I came to CU. And it was that I never thought that would actually be really useful for me in an astronomy and a physics career. But I was amazed how much writing you have to know how to do, and how much networking and like public speaking and all sorts of different skills that I used, in a business world or in my other undergraduate degree, that all come into play. You're not just the typical scientist like sitting at your computer in your little lab coat or what have you. There's so much more to it than that.
Sure. Hey, you guys were asking about outreach. We should take a moment to talk about the big I, right? Imposter syndrome.
Ooh, yes.
Right. Everybody feels that they don't belong, right? A big part of getting into science is learning to lean into that feeling of, I'm not quite sure what I'm doing here, right? My colleague Hal Levison, who's also works at Southwest, used to say, to be a good scientist, you have to enjoy feeling stupid, right? Most people feel stupid and sort of veer away because they want to feel that they're smart or important. And again, that's something you train yourself to do, right? To dive into that feeling of stupidity and enjoy it, because it means there's something interesting to do there, right? Something to learn.
That is definitely something I have felt in research.
Oh yeah.
I have no idea what I'm doing.
Sorry, I got something in my eye here. But exactly, yeah. I think that's why we lose a lot of folks from sort of the broader backgrounds. People who sort of, maybe they're the first in their family to go to college, right? Or maybe they come from a family that's got more sort of, poetic gifts as opposed to hard science, mathematical gifts. And they think, I don't belong there, right? Maybe my skin color is different than most of my classmates, right? But the thing that, if there's one thing I've learned from 30 years in this field and watching people grow into it, is nobody feels like they belong, right? Everybody gets imposter syndrome, right? Because you're in your head trying to learn something, right? And it's hard, and you're facing your own challenges, and you see other people who look like they're gliding through it. You don't see the struggles they're going through, right? And so it's almost impossible to avoid or to overstate. Everybody feels like they don't belong when they're learning these things. And so, overcoming it is a huge thing.
Thanks for pointing that out. I feel like there's a lot of, especially in education, well, because that's what I know as of my life right now,
Yeah.
that conversation, I think, could happen a lot more often than it does. And of course, that's not backhanded. I think it's easy to forget that is such a big part of learning for your whole life, no matter what you're doing. And so thanks for, bringing that up in a space where we, at least hopefully, are reaching a lot of people who are actively engaging in learning these kinds of things. As a
Sure.
reminder, that's okay and normal and good.
You mentioned your 30 years in the field and seeing things change. How have things changed in the 30 years that you've been doing heliophysics?
Oh my gosh. The biggest thing is my beard's gray now. I have to tell you, it's hard to believe it's been that long, right? You get wrapped up in a couple of questions, and all of a sudden a decade has gone by, and then another one. I don't feel much different than I did in my late 20s in terms of, trying to get interested in problems. I have more tools to draw on. But the field itself has changed quite a bit. In 1991, solar wind physics was a different field than solar physics. Right now we have two missions that are designed specifically to unify those. We have Punch, which is bringing imaging science outward, and we have Parker Solar Probe that's bringing solar wind science in to sample the corona. The mix of people has changed. I remember, oh my gosh, working on SOHO. This is a big mission in the mid-90s, my first mission out of graduate school. There were a handful of women in that science at the time on the team. And I remember one of my colleagues getting asked to make coffee, right? One of our European colleagues came in and just assumed that she was the secretary. And it didn't end well, but people live and learn. But so the balance of the gender roles has gotten much better. I think we're more diverse in the sense that there are folks from a lot of different backgrounds who are sort of breaking into astronomy and solar physics. And these are things that again, it takes a decade or so to happen. So in the moment you see the struggle, you don't see the progress. But looking back across the 30 years, it is really great to see the progress that we've made in terms of trying to break out of science being, for well-to-do white men, right? Which it was for a very long time.
And I also saw on the website, even just the leadership team that you have is including a lot of international scientists, not just people from here in the United States and from NASA. Does that make things a bit more difficult having everybody so spread out like that, or bringing in international groups?
Having the science team spread around the world is hard. It's much less hard during COVID, ironically, because everyone's on video anyway, right? So it becomes a time zone issue. But in terms of just diversity of background, diversity of approach and age, all these things are important. You familiar with Anton Chekhov? He's a playwright.
Yes, absolutely.
Okay, so there's this play that I like to refer to, the Cherry Orchard, right? And in the Cherry Orchard, it's a really disturbing play. And the reason it's disturbing is anyone in their right mind wants to leap up on the stage and throttle the main character, right? There's this impending doom coming. Everybody can see it. Everybody on the stage can see it except the main character. Everyone in the audience can see it. It's like a Mack truck with the horn blowing, right? And it's just invisible to that person. But the lesson to take from the cherry orchard is we all have blind spots like that, right? There is something you can't see in the world, and you don't know where it is because you can't see it, right? So the best way to avoid that is to surround yourself with people with different blind spots than yours, right? And so if you're part of a team that has radically different approaches to the same problem, the likelihood of getting blindsided in that way is much less. That's, if for no other reason, that is worth the whole ticket price for the cherry orchard. So there, I saved you a ticket.
I'll look around and see if any troops are putting it up, you know, coming this upcoming season here.
There you go.
Someone always is.
Yeah, the cherry orchard. Craig, something that we discussed, and for our listeners, I'm going to break the fourth wall here, which is kind of a weird idea because we refer to you as listeners. So I don't know if there was one to begin with, but you know, we kind of always do some research and you know, dive in a little bit before we do these podcast episodes. And something that came up in talking with another member of the Punch team was the emphasis on the human aspect of the scientists involved in the mission. And so that was a long way of me prepping the question. Craig, would you tell us about your farm?
My farm? Wait, I don't have a farm.
Don't you? Well, I have to ask myself then where that came from, because I have written down.
I like to refer to Stanford as the West Bay Farm School, which is sort of a joke. They refer to it as the farm. So that may be what happened.
Well, please excuse me. I perhaps my notes for this and someone else have overlapped in a way that they weren't supposed to. In that case, let me ask you then about your history and, you know, starting as a kid, what brought you to being in this Zoom meeting with us today, talking about your role as the PI of Punch?
Sure. Wow.
Farm or not.
It goes way back. You know, everybody has a story that's like how I got into my field. And I have a really pat one. I was in the Boy Scouts as a boy. I remember in 1980, 79, something like that, going on a camp out and getting up at dawn. And it happened to be solar maximum then. I didn't know what that was. Maximum activity period. And I watched the sunrise and there was a spot in the middle of it. I remember asking my old man, who was a space physicist, you know, what it was, and he told me about sunspots. Of course, some other guy named Sting saw the sun at around the same time and wrote a song about that, which was a pretty cool song. I mean, that's a pat story, and I used to tell that story, but it's wrong. It's not why I'm here. I mean, that is a moment I was interested in solar physics as a boy. I think you have to kind of, you follow your muse. I kind of followed my muse 5 years at a time. Probably, my old man was a physicist, and I tried my hardest to get to not be one, and it failed utterly. But he used to tell me, don't plan more than 5 years in the future. Say, what would I like to do in 5 years? And let that person sort out what they want to do, because you'll be somebody else by then anyway. Right? So I tried to keep doors open for that guy. I remember in my liberal arts college, studying physics specifically because I knew that I was interested in physics and other things, but I could do those other things as a dilettante, and I couldn't really do physics as a dilettante. So I had an interest in journalism and an interest in art history and, you know, a bunch of other things. But, you know, anybody can go to an art museum right? But you can't just go to a particle accelerator and learn new things, right? So in college, I tried to pick things that would sort of keep my options open later. As a senior, I knew I wanted to go to grad school, and I picked a school that had 3 different programs, any one of which was really interesting. The real reason I studied solar physics is the community. And you know, this is useful to people who are considering graduate school, right? If you're a smart person and you work hard, there are lots of interesting problems in the world, right? Gravity waves, astronomy, solving, you know, how to make solar panels more effective, right? And there are a lot of really interesting problems you can devote your life to. But you're going to have to live with the people who are also studying those problems, right? So find a group of people that you want to spend time with, because you're going to have to. Solar physics at that time had a much more collegial community than, say, particle physics. And there are a number of reasons for why that was. But I found that group of people, and I saw that the organizations were very supportive on multiple scales. And people saw each other as colleagues rather than mortal enemies. And so that guy, who was picking a subject at the beginning of graduate school, picked solar physics. After that, you know, the next guy picked the next thing.
I think that's very insightful to think about, you know, kind of planning out your life 5 years at a time, because I think it's daunting, especially going into college and also, you know, leaving college, trying to think about it all as one whole big path for the rest of your life. But it's absolutely true. You end up becoming a very different person in 5 years who will absolutely want something different, and be, you know, in a different spot. So it's a very cool takeaway. Craig, I think we're about that time in our interview, but before I say thanks and let you go enjoy the rest of your night, was there anything that you were looking forward to talking about that we didn't touch on yet?
Well, this is, I mean, there's always more directions to go.
Always.
We talked about the technical aspects of Punch. There's a website, punch.space.swri.edu.
Swri spelled SWRI.
Right.
Right.
Thank you. Thank you. We're planning to launch in 23. We are right now doing deep background, but there are a lot of folks who are preparing for the Punch launch. And so if you are a graduate student and you're interested in Punch, drop us a line. We're all friendly and we don't bite. If you would like to see some images of what we can do, the Punch website has prototype images made with existing missions that sort of show the kinds of things we'd like to look at. That's really great. If you are considering a career in STEM, right, branch out, study as much about communication as you can. It'll give you a leg up. Everybody else going into physics will be avoiding those classes, so you get a competitive advantage. And remember to have fun, right? This is fun. We're here bettering humanity and also having fun at it. So, you know, remember that, it's important. I guess to close, thank you guys. This has been a really fun hour. Thank you.
Craig, thanks so much for giving us your time and telling us about this very cool mission that you are working on.
All right, everybody, that wraps up our episode for this week. We want to say thank you again to Dr. Craig DeForest. It was so fun to chat with him. He had so much cool insight and advice, and he was just a great guy to talk to. That was really fun. We also want to make sure that you come back next week because we're going to be talking with another member of the Punch team. This is Mary Hansen. She's the student project manager for Punch. So she kind of coordinates a group of students that are helping the Punch team with a specific instrument. And she's the sort of liaison between the students and the scientists and does a lot of really interesting stuff herself, like balloon experiments, which I think is neat. So be sure to check that out. If you want more information on our upcoming episodes, or if you want to find any of our old episodes, you can do that on our website, www.colorado.edu/Fiske. There you can see the schedule of old episodes, upcoming episodes with topics and guests. There's also an option there for you to submit questions for our experts to answer about any of our upcoming episodes. So if you see anything there that strikes your interest and you have a question, shoot it to us. We'd love to hear from you. You can also send us an email at fiskepodcast@colorado.edu. We'll love to chat with you that way too. Also on our website, there is an option where you can donate to our podcast. If you really want to help us keep going with the podcast and making these episodes and bringing you these really fun and insightful interviews, we would love a little bit of financial assistance with that. We are motivated, and basically we do this because of viewers like you. So we thank you in advance for any donation that you may be able to give us. Also, don't forget to like and comment and subscribe on our episodes, share them with your friends. Make sure you subscribe so you don't miss any of the upcoming ones. And we are available on YouTube, SoundCloud, Spotify, and Apple Podcasts, and also again on the Fiske website. So you can check us out in any of those formats. And we hope that you do, and we hope that you see you again next week.